Hello, so in this video I'm going to talk about Half-Life again. This video is for you if you are in Algebra 2 or higher, if you watch this video and you feel like you can handle this math no problem, or you just find it really interesting. That'd be great. So the half-life equation that we're going to be using now is more complex than we have used previously. It's an example of exponential decay, and if you're in Algebra 2 then this will probably look very familiar. The idea of b is as a constant. In this case it will be a half because we're dealing with half-lives. And remember, the definition of a half-life is how long does it take half the sample to undergo radioactive decay. So the constant in the exponential decay version would be 1/2, and then x is the elapsed time divided by the half-life, so how much, the ratio of the time. And so I'm not going to go through the long derivative to get to this. If you're in calculus, then perhaps you might want to do that, but I'm not going to. But we end up with this equation, which is what we'll be using for exponential decay. And there are some notes that go along with this video, so you don't have to memorize it, write anything down from this video, you can just check the notes. But the idea is, n subscript t stands for the amount of time, amount of substance that remains, so the amount of the sample. This would be how much you start with, n0. 1/2 is the constant, and then it's to the power of the elapsed time divided by the half-life. So it does have some similarity, but in this version we need to take into account how much we start with, so that's why we multiply by the initial amount. So then what we'd have to do is plug the numbers in. So for example, with this problem we've got, or it tells us that we start with 500 grams, we're dealing with carbon-14, which is radioactive. So how much would we have after 2,000 years? We would need the half-life for that, which is 5,730 years, give or take. So what we do is plug in all the numbers and then solve, which we'll do really, really quickly. And then I'll talk about, again, if you're feeling like you want more challenge with this kind of problem, or in math and or chemistry, then I'll talk about what you can do next. But basically what we do is just plug in the numbers. So we start with n subscript 0, which is 500. I'm going to multiply that by 1/2 to the power of 2,000, which is the elapsed time, divided by the half-life, which is 5730, or 5730. So we'd have to multiply and then take 1/2 to the power of that, and then we get our solution. Just looking at the numbers, 2,000 is not too far away from exactly 1/2 of this. So maybe in your head you can do a little guess and check, maybe, of how much you'd actually end up with. So one half-life would take us to 250. So if we go half of that time in years, then we'd probably end up with like 375-ish, very, very roughly. But that's just a good tip when you're dealing with these kind of problems. It's good to have an idea what it would be eventually. So then the other thing to say about this kind of problem, I'm not going to do this, you can just plug that in your calculator. But the other thing to say about this is that we can manipulate algebraically to solve for elapsed time, if we know everything else, half-life. Although usually half-life is on a table, it's usually given to you, so you don't need to memorize that, or it will be given to you in the problem. Starting amount or ending amount. So basically we can manipulate however much we need to. Just erase this. I'll go through that really quickly. Maybe if you're not in Algebra 2, you might just be curious of how we actually end up with that. There are some written notes that go through it, but just to take you through it. I'm not going to go into too much detail on logarithms, just for the interest of time. But if you are more interested in logarithms, then definitely let me know, and I'll point you in the direction of some fun resources to deal with. So let's say that we want to solve for the elapsed time. So it's kind of tricky because it's to the power and it's divided by something, but let's just start with the easy things. So if we can move this over to the left, so if we divide by NO, So then that would give us nt divided by n to the subscript 0, and that equals 1/2 to the power of t divided by its half-life. So then what we'd have to do next is take a logarithm of both sides, and so we could do that. So the log of this is equal to the log of 1/2, and then that would bring this power down, so we've taken care of this exponent issue by taking the logarithm. So then we could divide, this is multiplying here, so we could divide by a log of 1/2. So we'll do that. So that will give us a log of nt divided by n0 divided by a log of 1/2 is equal to the time divided by the half-life. And if we're solving for the elapsed time, then we can just multiply by the half-life. And then we end up with the elapsed time is equal to the log divided by log So you could also do that if you were solving for the starting amount, if you were trying to calculate the half-life and maybe identify the element. Usually most elements just have a unique half-life, and so you could identify the element if you knew the half-life, or at least narrow it down. But that's how you manipulate to get to solve for t, and you'd also use a very similar approach to solve for the half-life. And so that's it. So the idea of this video, again, just to re-emphasize it, if you're interested in this and you want to go a little bit further than just solving half-life in the way that we'll go through in class, then this is just a little step up. I've deliberately missed off a lot of the algebra, but just to keep it maybe to the point where if you're in geometry or whatever, then you can easily deal with this. So half-life is an example of exponential decay, and again, just to show you that, we'd actually have a curve, and it would basically go really, really close to the x-axis. It would never touch, because the idea that you will always end up with some, even if you, after a certain amount of time, half is gone, right? So you're reducing the amount by half, and then a half again, then a half again, half again. So you'll always end up with a number, or an integer, positive integer. Anyway, so the idea is we can manipulate. There's a derivative for this version right here, which I'm not going to go through now. I got through a bachelor's in chemistry without knowing it, so but it would help. But you can manipulate this to solve for any of the other variables, and that's it. And if you go back to the notes that go along with this video, there's examples that you can go through.